In this video, we introduce the Laplace Transformation Operator and the Laplace Transform f of s of a function f of t. We're going to start with a discussion of operators and transformations, and then I will define the Laplace Transform f of s of a function f of t, and then we'll work an example problem. So operators or transformations are very similar to functions. Here's an example of a function, f of x equals x squared. F of x equals x squared takes a real number, x, and then it maps it to another real number given by x squared. Or we can think of it this way. It's taking an x value and then mapping it to a real number given by that number squared. So a function takes a real number and gives you a real number back. Operators or transformations are similar, but instead of taking an number as an input and giving you a number back, operators or transformations take a function as an input and they give you a function back. We can think of these as operating on a function and they yield another function. Or you can think of it this way, we are transforming one function into another function. That second one sounds kind of magical. It's not magic, it's just an operation. Now you're already familiar with some operators. In Calculus 1, we taught you about this operator d dx. If you have d dx applied to some function, you are taking the derivative with respect to x of whatever that function is. So this is the differentiation operator. So let's say we put our input here as x squared. Well, this operator operates on x squared and gives us back this new function, 2x. So we would say that this process of taking the derivative of x squared and getting 2x is called differentiation. And this is the differentiation operator. And then we say that this function is the derivative of this function. So we'll say that 2x is the derivative of f of x. Or in general, we say that f prime of x is the derivative of f of x. Now sometimes rather than using this d dx operator, you'll see it denoted this way, d for derivative. Sometimes in order to specify what that variable is, you'll see it with a subscript x, d sub x being the derivative with respect to x. So if I wanted to use this operator notation rather than this operator notation, I might write it this way. The derivative of x squared is equal to 2x. It's acting on a function and giving me a function back. So I'm thinking of that as an operator. I can also think of it as a transformation. It's transforming this function x squared into this other function 2x. So it's acting on a function of x and it's giving me a function of x back, and that's what makes it an operator, that it's mapping from a function to another function. Another operator that you're familiar with is the antiderivative operator. This one's a little bit harder to draw because it needs to have something inside here. So I will call this the antidifferentiation operator. The process of computing an antiderivative is called antidifferentiation. If I want the antiderivative of x squared, we use a power rule. So we add 1 to the exponent, and we divide by the new exponent, and we add c. So we're acting on a function x squared, and then the output, is a function 1/3 x cubed plus c. Now we could use this notation as well. It looks like a d to the -1 or d inverse. That's intentional. If this is the differentiation operator, the anti-differentiation operator is d inverse. Or if you're trying to specify that that's a differentiation with respect to x, you might use a subscript there and then put inverse symbol here to say that we are taking the antiderivative of something with respect to x. So rather than writing this, we might write this. The antiderivative of x squared is 1/3 x cubed plus c. This is acting on a function x squared, and it's giving me the function back, 1/3 x cubed plus c. So in that case, we would say that 1/3 x cubed plus c is the antiderivative of x squared. Or in general, we might say that the antiderivative of f of x is equal to capital F of x plus c, where the derivative of this function is equal to this function. So f of x plus c is the antiderivative of f of x. Now, most of the time, that last line is written this way, as you saw way back in Calculus 1. So the antiderivative operator or antidifferentiation operator operates on a function of x, and it gives you a function of x back. And the derivative operator acts in the same way. Now, this chapter or this unit about the Laplace transformation does something similar. But rather than operating on a function of x and giving us a function of x back, the Laplace transformation is typically written so that it operates on a function of t and it gives us a function of s back. So let's say that we have f, and f is a function of t, and f is defined on the interval from 0 to infinity. Then the Laplace transform of f of t is denoted this way. You have that L symbol, that's our operator. It's acting on the function f of t, and it actually gives us a function f of s back, and it's defined in this way. It's the integral from 0 to infinity of e to the negative st times f of t dt. Now remember, this integral is an improper integral because that upper bound is infinite. So if I'm actually going to evaluate this, I need to write it as a limit first. Since the upper bound is infinite, I'll take the limit as b goes to infinity and replace that infinity with a b. So the value of an improper integral is always the limit of a proper integral, like this. So in practice, when I'm computing the Laplace transform using the definition, what I do is I evaluate this expression first. And remember, here we're treating s as a constant and we're anti-differentiating with respect to t. So we're going to compute an antiderivative with respect to t. Then we're going to replace t with 0 and b, and then we're going to let b go to infinity. After we do that, all of the t's will be gone from here, and all we will have left is a function of s. That's capital F of s, and capital F of s is the Laplace transform of little f of t. I'm going to call this little f of t and this big F of s, even because I don't like saying lowercase f of t and capital F of s. I just like to call this little f and that big F, but that's the convention. We use a lowercase letter for our functions of t, and we use our uppercase letter for the Laplace transform of those functions, and those are always functions of s. So this is our definition of the Laplace transform. Laplace transform of f of t And in practice, we're going to evaluate that this way. We say that L is the Laplace transformation and that's a Laplace transformation operator. A transformation and an operator are the same thing. So this is operating on a function of t and giving us a function of f or of s back. We say that f of s is the Laplace transform of little f of t. So it's kind of like we were just saying with the differentiation operator and the anti-differentiation operator. The process of taking a derivative is called differentiation. The process of taking an antiderivative is called anti-differentiation. The process of computing a Laplace transform is the Laplace transformation. And we think of this as the Laplace transformation operator. And we think of ddx as the differentiation operator. We think of that integral with respect to x as the anti-differentiation operator. And the derivative, the antiderivative, and the transform, Laplace transform, those are the functions that result after that operation. So I'm just trying to make sure I use my terminology correctly. The transformation refers to the process of computing a transform. And this L is an operator, which we would call the Laplace transformation operator. But the function f of s itself is called the Laplace transform of f of t. Now, s is called the transformation parameter. In general, s is a complex number. So s can be written as a constant plus I times a constant, where those two constants are real numbers. But in this class, we're going to think of s as a real number. We'll say we'll consider s to be a real number. Now, just to apply this definition that we talked about, I'd like to do an example. So let's say you have a piecewise function f of t, and maybe it's this. Maybe it's t minus 1 for t between 0 and 2, and then it's equal to 3 for t greater than or equal to 2. Since this is a piecewise function, if I'm using the definition of the Laplace transform, I'm actually going to write this as the sum of two integrals. So we're computing the Laplace transform of f of t using the definition. Now, if I wanted to, I could graph this. When t is equal to 0, f of t is -1. When t is equal to 2, we're going to have 2 minus 1, which is 1. And it's going to be an open circle there. And so the function would look like that. And then from 2 on, 2 to infinity, the y value on this graph is equal to 3. So let's say that this is my function f of t. and I want to compute the Laplace transform using the definition. Well, I could go from this to this graph, and then I can just use the definition this way. So this is the integral from 0 to infinity of e to the negative st times f of t. And we're taking the integral with respect to t, not s. Now, because f of t is defined differently on these two intervals and these two branches, we can write this as the sum of two integrals. So this is going to be the integral from 0 to 2 of e to the negative st times f of t. And when we're on the interval from 0 to 2, f of t is given by t minus 1. Oops, I wanted to use red there. And then on the interval from 2 to infinity, f of t is given by 3. And we're splitting it up like this. Oops, I guess I should have put a 3 in there. That was my intention. We're splitting it up like this because the integral from 0 to infinity is the same as the integral from 0 to 2 plus the integral from 2 to infinity, as long as we have the right function f of t there. And on this interval, f of t is equal to t minus 1. And on this interval, f of t is equal to 3. So this is actually just a regular integral, an ordinary typical integral that can be evaluated using integration by parts. And then this piece over here is actually an improper integral. Since I have that infinity right there, I need to write that improper integral as the limit of a proper integral. So we'll take the limit as b goes to infinity of the integral from 2 to b of 3 times e to the negative st with respect to t. Okay, so now we just need to evaluate this and then evaluate this, and then we'll be done. Now over here, because I've got a polynomial times an exponential function, I think the easiest way to evaluate this is to use integration by parts. So I'll let u equal the first function, and dv will be the second function. And since my u is a polynomial, the easiest way to evaluate this is to use integration or use tabular integration. So u is t minus 1, then you take the derivative and you take the derivative again. And then dv is e to the negative st. The antiderivative of e to the negative st is e to that power. And since there's a constant times t here, and we're thinking of s as a constant because we're taking an antiderivative with respect to t, the antiderivative of e to some power, when that power is a constant times your variable, is e to that power divided by the constant. If I were to take the derivative with respect to t, I'd have to multiply by a negative s by the chain rule. Since I'm taking an antiderivative with respect to t, I'll divide by negative s by the chain rule. And every time we take an antiderivative, we're going to multiply by another negative s because the exponential is still there doing the same thing every time. So when I take the antiderivative again, I'll multiply by another negative s, and I get a negative s squared there. And then we'll have the sign convention plus minus plus over here on the side. Okay, so according to tabular integration by parts, the integral of t minus 1 times e to the negative st dt is this quantity times this quantity plus this times negative 1 plus c. And then we would evaluate from 0 to 2. Since it's a definite integral, there's no need to write the plus c. We'll just write negative 1 over s times t minus 1. And I'm going to factor out that e to the negative st minus 1 times 1 over s squared. And all of that is multiplied by the e to the negative st. And then we're going to evaluate that from t equals 0 to t equals 2. Okay, at t equals 2, we're going to have 2 minus 1, which is 1, times negative s, or negative 1 over s, minus 1 over s squared. And that's all multiplied by e to the negative st, where t is replaced with 2. So it's going to be e to the negative 2s. And then we'll evaluate this expression at t equals 0. So we'll have -1 times -1 over s is +1 over s. Oops, we're subtracting, sorry. Minus 1 over s squared times e to the 0, which is 1. So that's the first piece. And then for the second piece over here, we're just going to do the same thing, but we had to write it as a limit first. Now remember, whenever you are evaluating an improper integral, the first thing that you need to do is write the improper integral as a limit or as the limit of a proper integral. And we've already done that. And then once you've got a proper integral, you can evaluate that using the fundamental theorem of calculus. Okay, so that's the plan. So let's do it. So I'm sort of ignoring this limit as b goes to infinity for right now, but I'm going to bring it down, just continuing to rewrite it every time. I'm not doing anything with it, but in order for everything to actually be equal, I need to carry it down. The antiderivative of 3 times e to the negative st is 3 times e to the negative st. Since there's a constant multiplying the t, we've got to divide by the constant. And then we'll evaluate this from t equals 2 to t equals b. So I'll take out that -3 over s, and then I'm multiplying that by negative s times b, so negative bs, if you will, that's fine, minus e to the negative, well, if t is replaced with a 2, that's going to be -2s there. And then you ask yourself, well, what happens to this expression as b goes to infinity? Well, it will go to 0 as long as this exponent is large and negative as b goes to infinity. And this exponent will be large and negative as b goes to infinity if negative s is negative or if s is positive. So this is going to go to 0, but it only goes to 0 under the condition that s is positive. So we have this plus this limit. So we evaluated the proper integral, and then we computed the limit. And that limit happened to be -3 over s times a -1. So it's going to be a +3 over s times e to the -2s. And that's being added to all of this over here. And actually, I think we've got some like terms. I've got a 3 over s times this and a -1 over s times that exponential. So we can clean this up a bit. This is going to be 3 over s minus 1 over s, which is 2 over s minus 1 over s squared times e to the -2s. That's this piece and this piece. And then we're subtracting this. And if you want, you could distribute the negative. You don't have to. That's minus 1 over s plus 1 over s squared. And that is the Laplace transform f of s of the function f of t, where f of t has this graph, or f of t is written this way as a piecewise function. It's t minus 1 on the interval from 0 to 2, and it's 3 on the interval from 2 to infinity. So that's how we apply the definition. I'll see you in the next video to talk more about the Laplace transformation.